Alrighty. Hey everybody, we're going to get started. So thank you guys all for coming out to the bigger space. Hopefully it seems like everyone will hopefully have seating now. So as I mentioned earlier today, this talk is going to dive a little bit deeper into the audio analysis API that Spotify provides through their public API. So let's kind of talk about audio. It's easy for people, and it's much harder for computers, oddly enough. It's easy for people to do things like find the beat in a song. But when a computer is given a raw audio signal, well, it's just zeros and ones and bits and bytes to the computer. So it's kind of difficult for it. We have to actually tell it how to interpret those bits and bytes and what a beat actually is. So like I mentioned before, we do offer a few higher level audio features. So things like acousticness, danceability, energy. These are all pretty straightforward, at least in terms of English. If you know what energy is, right, higher energy music is going to be a little bit more upbeat. It's going to have a higher tempo. It might be louder, so on and so forth. Instrumentalness is going to kind of be a range of information about how instrumental a track is versus lyrical. There's also things like key, liveness, loudness. Now, how are these numbers actually presented? This is what the JSON response from the web API actually looks like for audio features. So danceability, energy, acousticness, instrumentalness, all of these things come back as generally ranges from 0 to 1. You'll notice that loudness is actually a negative number. That's loudness in decibels. So in this case, it's negative 5.31 decibels. Or it's kind of a rating, I think it's average decibel over the entire course of the song. Liveness, valence, tempo comes back as beats per minute. This information is all provided in the public web API, which is a good thing. The audio analysis stuff that I'm talking about a little bit in a few slides is a little less documented, so I'm going to dive a little bit deeper into that. One thing to note about these audio features and these high-level features is that they're not necessarily as straightforward as you think. So acousticness is a probabilistic distribution of how confident that we are that a song is purely acoustic, as opposed to electric or something like that, or synthesized. So you notice the probability or the distribution of tracks with zero acousticness is actually really high. So we do have high confidence for a lot of tracks, but we have a long tail for lower confidence of tracks that are acoustic. So you want to take it with a grain of salt. It's supposed to be a binary indicator, right? And you can be pretty sure that tracks with a zero acousticness level definitely are not purely acoustic. But any tracks with above 0, they could be, and the higher the value, the less sure we are that it's definitely not acoustic. Or is it? Definitely not acoustic. Binary classifiers, zeros and ones, things like that, and ranges. So danceability, you can see, is a more kind of normal distribution. This one's a little bit more like, okay, it's not trying to be, is this danceable or is it not? So you can see the middle is where most of the songs fall. Most songs are like reasonably danceable. Some songs are really not. They might be too slow. They might be too noisy. Those will fall lower on the danceability scale. And songs that are like classic dance music, everybody, you pretty much hear it on the radio and you have to bob your head because it's so good. That's what's going to fall on the higher end of the spectrum there, or at least what we aim to provide on the higher end of the spectrum. Instrumentalness, as well as speechiness, are also more attempted binary classifiers. So things that are 0 in instrumentalness are definitely not instrumental. The higher the value, the lower confidence we have about that information. So theoretically, anything that's above 0 could be instrumental. But if it's 0, it's definitely not instrumental. And that's the way to kind of interpret that. And same thing with speechiness, whether or not this contains speech or is purely speech, that's the goal of the speechiness indicator. So lyrical or kind of like verbal interludes of tracks will definitely be higher on the speechiness value. Things with 0 mean that there's no real pure speech in it. And that's an important thing because you don't want like bonus tracks or JFK speeches to show up in recommender systems. So you want to pay kind of close attention to things like that. Valence is essentially how like happy or sad a track is, and it's a very subjective term. So take that with a grain of salt. But we try to predict, happier music will be closer to 1, and sadder music will be closer to 0. So if you're trying to match a mood, figure out where you want that mood to lie. And liveness is the probability distribution that we think a musical piece was performed live or not. If you have live music in your library or some live pieces that are on Spotify, you can play around with the values to see what that looks like. So this is where we're going to get into the real meat of the conversation, is audio analysis. This is the kind of hard stuff. It's the stuff that's not super well documented on our API yet. I'm going to work on that after this talk. But we're going to look at things like bars, beats, sections, segments, pitches, timbres, tatums, and echo print data. So these things are all provided through the audio analysis API. And we're going to cover a little bit about what those things are, as well as kind of how to use them. So you might be asking, like, what is a tater? Or actually a tatum, rather. Not all of these terms are like super canonical or well known to people who aren't familiar with music theory or have deep music knowledge. So I'm going to give a little bit of a music terminology crash course. Bars, beats, Battlestar Galactica. If anyone watches The Office, that's an Office reference. Right, sure, he knows music. So who here knows what a time signature is? So that's a pretty good number. Can someone tell me what a time signature is?
How far is the beat per measure? Bottom number is
Sure. So the top number of a time signature indicates how many beats we have per bar or measure, and the bottom note is, the bottom number is what note gets a beat. And in this case, it's going to be 1/4, which is a quarter note. So these are all quarter notes, and they each get a beat. And so you get, in this case, if we were singing Old MacDonald in 4/4, some people will probably say that Old MacDonald Had a Farm is not in 4/4. They're probably right, but for the sake of this demo, we're going to pretend that it is. So in this case, if we were looking at a quarter note per beat, it would be Old MacDonald had a farm. And so you see that Don gets its own beat, Old gets its own beat, Mac gets its own beat, and there's 4 beats per bar. If we wanted to just clap on the downbeat, which is going to be the first beat of each bar, it's going to be Old MacDonald had a farm. Just some useful information to know. The upbeat would be on the Ald. There's no second upbeat. And in this case, the bar is going to be what you see between these two lines, right? So here we go. A beat is smaller than a bar. And, well, we're not going to talk about tatums yet because they're not really represented in standard sheet music. But as you can see, the other tracks down here, so for instance, Yankee Doodle is in 2/4 time signature. So we get 2 beats per measure instead of 4. And still a quarter note gets a beat. So it's going to be Yankee Doodle went to town riding on a pony. So there's a little bit of a difference there because key is not going to get a beat. It's Yankee Doodle. So just something to know. And this is important because, as I said here, we get bars, beats, and things like that. So you want to know what each of those things mean when we start to interpret them. So this is what the audio analysis information breakdown kind of looks like. So this is Around the World by Daft Punk. Does anyone here know that song? It's a kind of a classic. The nice part about it and why it's really useful for this demo is because it's in a really clear 4/4 time signature. You can hear the beats very clearly, and the tempo is pretty nice, right? It's 121, which is just about 2 beats per second. And so here, on this graph, you can see we have beats in red, so those are our plus signs. We have bars as these stars up here. So we see, there's generally a star every 4 beats. As we said, we're in a 4/4 time signature, so that corresponds appropriately. And now we have this word tatum. Does anyone know what a tatum is? So tatum is kind of, it's a term that's somewhat common among digital signal processing and audio analysis. but it's not super well known to people. What a tatum is generally the smallest pulse that humans can conceive. And so we're going to explain that a little bit more in a second. But in general, it's going to be around half of a beat, or if a song is swung, there might be proportions of like when tatums fall. And that's kind of why tatums are useful, is for determining string music and how swung a song is. Additionally, we have this confidence, that gray line. And this is going to, I'll kind of explain a little bit more about that later. But basically, these are all estimates and predictions. So you should always factor in confidence into whenever you're using this data. Because it's available, we're not 100% sure what a beat is, right? Like I said, it's easy for humans to determine what a beat is, but this is a computer. So we have some measure of like how sure we are that this is in fact a beat or a bar or a tatum, or a section or segment. Furthermore, we have sections, which is ways to theoretically break down a song by maybe a chorus or a guitar solo or something like that. So how these generally look, at least with bars, beats, and tatums, the data that you're going to get back looks like this. So we have start, duration, and confidence. Now, you're going to get back a start, duration, and confidence for bars, beats, and tatums. In particular, this is like the second and third beats of around the world. So what you'll see here is we have the start time of the chunk, which in this case is, for the first one is 0.049, duration, which is 0.49 seconds, and then a confidence. So we're pretty, 0.978, it goes up to 1. We're pretty sure that this is in fact a beat. And then we get that again here, 0.99, 0.94, 0.493 for duration. And again, we have a pretty high confidence about this. So you can decide for your own use what is a good threshold of confidence for each of these things. But it's important to take that into account. So here's what beats actually look like. And in this case, the beat is the basic time unit of a piece of music. For example, each tick of a metronome. So this is actually a waveform of around the world. And what I've highlighted here are the spikes that we have determined are actually beats. And they do correspond to those numbers that I was just showing you. So if I actually bring up Audacity, let's see. So I'm going to play this, and what I want you to kind of watch is we have a little gray cursor that's going to be going along here. And when it hits the beat, see if you can kind of actually hear where it hits in that waveform. I'm going to restart that because it started. So as you can see, as it follows along, each time it hits that spike, it's like. So we see these big spikes, right? And that's pretty clear that those are beats. We can hear it. But what maybe you're not really hearing, and what it seems like we're not really clapping on, is maybe these kind of middle layers here, right? Now, this is what we call a tatum. A tatum is generally smaller than a beat. And it's the lowest regular, it's defined actually by, I guess, the guy who created the Echonest analyzer that we use for the Spotify API as the lowest regular pulse train that a listener intuitively infers from the timing of a perceived musical event. It's pretty wordy. Basically, it means like the smallest kind of pulse that you can hear in music. Now, if you listen closely to Around the World, you don't actually just hear the beats. You kind of hear something in between. And I'm going to clap along with that now. If I can. So we have the beat. Here comes tatum. So that's what a tatum sounds like. And as you can see, we have these beats here, but there are smaller pulses in between. And a lot of music does have kind of extra sounds on the tatums. This is important for a multitude of reasons. In reality, tatums aren't used super often in things that like change colors and things like that on the beat. Beats are much more usable because they're much more detected by the human ear. Tatums, you kind of have to think about. But tatums are useful for determining things like how swung a track is and things like that. Bars are as I said, a count of beats. And in this case, here's the bar for around the world. Although I think actually I might have messed this up. I think these, I think this actually might be 2 beats instead of 4. Actually, no, it's a bar. This is the correct bar measure. Shouldn't have second guessed myself. But this, well, if you hear it again, and if I plug this correctly, you can see it's the kind of wider gaps, and it's just a collection of beats, right? It's just a certain number of beats. But in this case, we have like bigger hits on each beat. So then we get into sections, which are kind of accumulations of bars and measures and stuff like that. But we define a section by large variations in rhythm or timbre, and it might look like you might define a section as a chorus or a verse or a bridge or a guitar solo, something that sounds drastically different from what was previously playing, right? So from chorus to verse, generally there's going to be some difference. So we try to predict what this looks like, so you can break down a song that way. Each section contains a bunch of its own information, such as descriptions of the tempo, key, the mode that it's in, like Dorian, Mixolydian, Ionian, things like that, time signature, and loudness. So this is a JSON response for a section. You're going to get a sequence of these, and they also have a duration. So for instance, this section starts at time 0, so it starts at the beginning of the song, and goes for just over 20 seconds. And we have pretty high confidence around that. One thing that I'm going to mention here is that I have personally found that the way that we define sections and the way that and the data that we return for sections is not super accurate. I personally wouldn't really consider the first 20 seconds of this song a true section because there is a very clear kind of difference between about the first 30 seconds and the first 40. So I'd really say the first 30 seconds is a section. So these are kind of subjective things. Take them as you will. Definitely try them out on your own. You might find that it works really well for some songs and not for others. But it does have a lot of useful information. Then we get into segments, which are a even smaller breakdown. And the idea behind a segment is where you're really getting kind of into the meat of this stuff. Because segments are this is a pretty wordy definition, a set of sound entities, typically under a section, each relatively uniform in timbre and harmony. Does anyone have like maybe a better way that they would describe that sentence? I do, but so I would generally describe a segment as a chunk of time that has generally the same sound all throughout. It's kind of persistent. So if you had a song that was pure piano, each, it's just a sequence of notes, each note theoretically would get a segment because each time you play a note on piano, it's going to sound pretty much the same throughout. So we try to make those into little pieces of time. And this is where audio analysis is really key because you have things like pitch and timbre, which is essentially a description of the sound for each of these segments. So if you wanted to determine how many times the C key was played in a song, then you could, or how many C chords were played. So these segments are kind of characterized by their perceptual onsets. So when it kind of starts to come in, how long it lasts, how long the loudness of it persists for, and as I said before, pitch and timbral content. So you can look at the JSON response. But what you notice here is that how do we describe pitches? It's a sequence of numbers between 0 and 1. It's not really documented in the API documentation about how to use these and what these 0 to 1 numbers means. And in fact, it's actually 12 numbers. So what does that tell you about the pitch? So pitch content is given by a chroma vector. And what it really is that this array of 0s to 1s, each of those indexes corresponds to the 12 traditional harmonic pitch classes, C, C sharp, D, to B, with values ranging from 0 to 1 that describe the relative dominance of each pitch in the chromatic scale. So, for instance, a C major chord would likely be represented by large values of C, E, and G. So they would probably all, theoretically, a pure C major chord would be represented by 1 in the 0, 4th, and 7th index. If you just had a pure C, nothing else around it, you would have theoretically a 1 in the 0th index. So that's how you can use pitch to kind of break down what's actually being played in this song. So there, once again, this is confidence, right? So we've predicted these values, but we're not totally sure. Sometimes there's musical interference. If you've worked with digital signal processing before, you know that frequencies aren't always clear. It depends on the bit rate that you have, and so on and so forth. So sometimes there's kind of some dribble out from other frequencies. So you might have a little bit of a D if you go from playing a D to a C major chord, well, you might still have a little bit of the D in there. So you can use these to break down what is actually playing within a given segment. And these vectors are normalized to 1 by their strongest dimension. So if you have a really loud C note and a little bit of a D, then C will come in at the strongest at 1, and then the D might come in at a little bit lower. Noisy sounds are going to be all 1s. So if it's really loud, if you're into metal or something and there's a lot going on in a segment, you might find a whole array of 1s. And as I said before, pure tones are described by a 1 value at the pitch and the others near 0. So a kind of visual representation of what this looks like is, well, each of the blue keys highlighted is a C on this piano. And so this is for those of you who don't know, what you see that line above is what's called an FFT, or a fast Fourier transform. And it's a transformation of the frequency domain into the time domain. So you can see this is over the course of, I think, probably 1024 samples. We noticed that the sum of these frequencies will comprise the waveform that we found in that sample range. And so you notice that these little red spikes or envelopes are what we consider C. And so if we had a C major chord or just a C note, theoretically you would see a pure spike under one of these red loops. And then you would get a pure 1 in the vector. And so you can see here that C actually is not a super prominent value in this segment. It's actually fairly low. But we do see spikes at D, G, and I think E, or whatever this note would correspond to. And so that's where we see these spikes. So as far as timbre goes, timbre is essentially how sound works in a short description. So if you play a C on a piano and then a C on a saxophone, who thinks that they could determine which one is which? Or at least determine that those are 2 different sounds, right? It's the same pitch, but they sound really different, right? And it has to do with the quality of the sound that comes out of it. The quality of the sound of a piano is very different from the quality of the sound of a saxophone. Now, it's really hard to represent this in data, right? We are humans, we can understand this, but computers, once again, just see 0s and 1s. So the way that we try to represent this through the Spotify API is by through a vector of 12 unbounded values that are roughly centered around 0. So these values can be as high as they want, but it's going to be an array of 12 numbers. Now, if you really want to kind of dig into this, the first dimension of that array kind of represents the average loudness of the segment. So louder segments will have higher values in the first dimension, and really quiet ones will have generally lower or 0 or even negative representations in the first dimension. The second dimension emphasizes brightness. So if you have a really bright segment, something that's very happy, something like a major chord or something like that, that would probably be represented by a high value in this second index. Third is correlated to the flatness of a sound. Fourth is to the sounds that have a stronger attack, so really like a big pop, so on and so forth. In reality, you shouldn't look at these and try to figure out exactly what all these numbers mean. The best way to use this timbre is to use them in comparison with one another. So you can probably compare these vectors using Euclidean distance. Another way would maybe be cosine similarity, but I don't think it's necessarily appropriate for this data. But if you want to try to figure out how many segments in a song, for instance, sound really similar, you can create a threshold for how far the Euclidean distance is. And that would say, well, this song has a lot of repetition in it because it only uses 3 sounds. If it's the same 3 sounds over and over again, it has the same timbre, same pitch content, then you could probably say there's like a lot of repetition in this song. These are the, if you know what spectrograms are, they are it's kind of an additional representation of an FFT with more FFTs included in it. And so, as you can see on the left, we have one spectrogram, and that's the spectrogram of our song. And then what we actually do is we take this through a PCA, which stands for Principal Component Analysis. And really all we're going to do is we're going to do dimensionality reduction. This original spectrogram has 460 floats per segment. So if we have a lot of segments in a track, it's going to be a lot of work. So instead, we take all these huge lists of floats and reduce them down to 12 dimensions because that's much easier to calculate and much easier to feed into something like machine learning models. It really tries to capture the most important aspects of what's happening in that spectrogram. And if you're really into spectrograms, we have these basis functions of what we use in order to do this dimensionality reduction. So this is your loudness, this is your flatness, et cetera, et cetera. And we result in these 12 floating segments that are generally centered around 0. So now I'm going to go into a bit of a demo, a few of them actually, and hope that my demo works. So I have a demo repository here that I kind of call the Hackathon Starter Kit. It gives you a big rundown on how to create an app, a registered application in the Spotify API. It tells you how to kind of get set up with this rundown. So if you just want to get started and start programming in Python using the web API, well, you can fork this repository, and it already has pretty much everything that you need in order to get connected. So let's run. So we're going to get some audio data. So we have 3 ways of choosing tracks that I built into this demo. So you can search for a song. Does anyone have a song that they want to see some audio features for? Right, well, I'll use
Gravity by Eden.
Gravity by Eden.
Yes.
It doesn't like that. Oh. Aha. So we're going to select Gravity by Eden, and then we have the option of we have open and close curly bracket tracks. So if we want to see, let's first look at the audio features, those high-level audio analysis. So it gives us the average tempo, the time signature, the key that we believe it in, and which in this case we think that it's B. And then you can see those values for loudness, energy, dentability, things like that. So this is the data that you get back. Now I've formatted this all nice so that we can see this in the demo, but this repo does actually just return it as a JSON response and a dictionary, so you can use it however you want. Additionally, we can choose from some playlists. So I'm going to enter my username. I have a lot of playlists. So let's see. I have my top 1,000 tracks. So I'm going to choose that playlist. And look at that, 1,000 tracks that I like. So if I wanted to get the audio analysis for some of these, I'm actually just going to do it for one, because I'm going to show you how huge audio analysis is. So this is audio analysis for one track. We're going to go fetch it from the API, and it comes back as a whole lot of text. And so remember, this is a list of segments, and I can tell because I have pitches and timbre. And so we get that for the whole thing, all the segments. You can use these as you will. It's a lot of text. And this is why we only allow you to request one audio analysis chunk at a time. So it actually overflows my terminal, so can't show you the top of it, but it looks, abbreviated form looks something like, so you're going to get some metadata on it about the analyzer, timestamp of when it was done, what the input process would look like for it. You're going to get the number of samples that we have for the track, duration of it. You're going to get this echo print version and some echo print strings, so that if you wanted to supply your own audio file, you could use the open source Echonest analyzer, or the public Echonest analyzer echo print tool to find your own echo prints, and then match it along with, and be sure that, like, hey, this Gravity by Eden, the one that I have locally, is actually the same one that Spotify was analyzing, or at least close enough to be used. We also have, a list of bars, like I mentioned before. We have a list of beats that are indented wrong. We have a list of tatums, sections, and segments. And so, remember what I said before. Sometimes things can be really noisy or really quiet. And in this case, the very beginning of Around the World is really quiet. In fact, it's pretty much no sound. So we have 1 for all the pitches because, as I said, they're normalized. So if there was no pitches, well, they're all going to be 1. So something to kind of be aware of. And that timbre, we see some big random values here. Not actually random, but they are representative of that sound. And so here again, we see pitches and timbre. So that is just kind of a way to get you started with the Spotify API. Then I do want to show you some of the stuff that you can use this for. So Paul Amir is a Spotify employee. He wrote Spotify, which is the open source Python Spotify API Python library. But he's also a really good hacker, and he's really great at understanding this audio and making cool things with it. So this is the song Levels. It's the Skrillex remix of Avicii's song. And he made this thing called the Auto Canonizer, which basically uses segments to figure out how you can write a canon of additional song, which is basically overlapping and remixing a song using itself. And so you can see this kind of green square just jumped back. So it uses some randomization logic to start playing parts of the song over with other parts of the song based on the segments and tatums and stuff like that, and the timbre quality profiles. So you saw that green square kind of drop down and slide over. That was it jumping ahead to another section that actually sounded similar. Very noisy, probably has very high, very high timbre vectors. So it's kind of remixing itself, and it's really cool. And it's doing this all using some randomization on top of the information provided by the Spotify API. Another demo that I think is really cool that he wrote is this thing called Girl Talk in a Box. And so there's a song, Fancy, by Iggy Azalea, and this is what it sounds like when Paul approaches it. So you have each of these squares, which is a segment. You can jump around, play it, and kind of just talk in a box. And so you can see Paul has done some cool work with kind of colorizing these segments by sort of what they sound like, and I think he actually used the timbre vector for this. So you see these light green squares, they probably all sound sort of similar to each other. so this is kind of a nice way to look at how timbre actually sounds the same. If we look at these kind of these maybe light pink squares. So I think this is a really cool demo and a really cool and innovative way to use this information. And there's a lot more that you can do with it. This is just one approach. And yeah, so let's see. I think that might be just about it. Those are the demos that oh, actually, there's one more that I wanted to show, and this is something that Hugh built. So if we have a track, let's say, let's look at that data that we have from Eden. My computer's struggling a little bit with it. 1 second. Demos never work, right? I'm going to try a different song. Let's see. So this is a breakdown of the relative time spans of the sections and bars. Refreshing. The sections and bars of a given track. So this kind of gives you an idea of you have sections, bars, beats, takedoms, and segments. There it goes. So as this line kind of moves across from the left, you can see when it hits each beat, section, bar, takedom. So as I said before, we have the first 20 sections of the segment, and or a section, and you're going to see that about to come to an end. There it goes. And so this is what I mean by like the sections aren't super accurate in my opinion. Maybe the song is a little bit hard because there's kind of an interleave between the sections. And so maybe that's why it doesn't catch it so well. This area is where I would say the start of the second section is, but the analyzer says that it actually starts a little bit earlier. So it's something to keep in mind. But if you're a little bit curious about what this stuff looks like, you can go to Spotify-audio analysis, Spotify-audio-analysis.glitch.me/analysis, and you can find this tool. And so this is where you can find the Hackathon Starter Pack. If you just Google Mark Koh Dev, M-A-R-K-K-O-H Dev, GitHub, you'll probably be brought to my profile, and you can find this there. Otherwise, you can maybe just Google Spotify API Starter and find it that way. Or you can go to the URL if you like going directly to URLs. So that's the talk that I have for you today. I'm going to be around for a little while afterwards to kind of, if anyone wants to use the starter pack and has any more questions on top of what is asked here, I encourage you to come chat with me about it or chat with you about some of the other stuff that's available in the API. And now I guess I'll open the floor for questions if I have a microphone somewhere.
Sweet.